Okay, so now we will be discussing about the VI characteristics of the PN junction diode. So basically we will be taking the help of the current equation which we have already discussed in the previous video. So I will be equals to, this is the reverse saturation current, and e to the power of Vd upon eta Vt minus 1. So here I have introduced the term that is the eta. Eta means what? IDDT factor. Now this is 1 for silicon and 2 for germanium. But if you just Google it, no, then you will be coming across that this is 1.44 germanium. So basically this is the equation which we are sought for. So now this will be, I will be equal to I0. This is the reverse saturation current, and this reverse saturation current will be in microamperes, and it is formed due to the minority charge carriers. Now what are the minority charge carriers? Which are small in number. So basically in the p-type semiconductor, you will be having this holes and the in the p-type semiconductor you will be having the holes and the electron. So this pp is very high as compared to the electrons in the p side, because we have added the boron atom, and boron atom will come with the vacant space or the hole. Now suppose if you add 10 lakh boron atom, then in that case you will be having the majority of holes only. Now similarly, when you talk about the n-type semiconductor, so n-type semiconductor means the number of the electrons are in majority and the holes are in minority. So number of electrons is very high as compared to the number of holes in the n side. Okay, so what we can say that the holes are the majority charge carriers in the p side, and electrons are the majority charge carriers in the n side. Fine, this much is clear to you now. Okay, so now we can see that this is Pn, this is Np. So already this term is very small, because they are very small in number. No, these are again, they are very small in number. So the entire product, we can say, it's a very small value. Normally it is a constant value. So what is going to happen now? Suppose if you are having the okay, we'll go to the PN junction diode. Now this is the PN junction diode. So this is in the no bias condition. Fine, because initially when we join the p-type and the n-type semiconductor, what is going to happen? These are the holes and this is the electron. Electron will try to diffuse through the PN junction. The moment we join the p-type and the n-type semiconductor, so this electron will try to enter into the outermost orbit of the atom, and in that case, and due to that, both electron and the hole will get vanished. So because of that, you have this depletion layer which will be depleted of the charge particles. Now in the semiconductor, the charge particles are electrons and the holes. There are two charge particles. So you can see here there are only atoms, there are no charge particles, that is electrons and the holes. So now if you want the current to flow, if you want to obtain the current through a PN junction diode, then you need to apply some forward biasing and the reverse biasing. So what is going to happen when you are applying a positive voltage? The positive current will flow from P towards N. Now how this thing is happening here? The forward biasing means what? Suppose you are having this one cell battery is there, this is positive, this one is negative. So when the positive terminal of a battery is connected to the P side and negative one will be connected to the N side, so in that case the diode is said to be in the forward bias condition. So now what is going to happen? You are applying the external voltage. So because of that, this voltage will be applied to this much length of the diode. So there will be a production of electrical field or the potential gradient. So here you are having the positive one and the electrical and negative one. So the electrical field will be directed from the positive to the negative. So we can say this as the external electrical field. So now you can see here the diode will be having two electrical fields. The first one is the internal electrical field, which is from N towards P side. You can see here this one is positive and this one is negative. That is the donor ion or donor atom, or this is the acceptor ions. So this is the internal electrical field. So slowly and steadily you will have to increase the increase the voltage, that is the external voltage. So what is going to happen? This electrical field will increase, the strength of electrical field will increase. So because of that, there will be a force of repulsion between positive and the hole, because these are like charges. No, like charges repel each other and unlike charges attract each other. So this positive will drift, or this positive will repel the holes towards the depletion layer, and they will attract the minority charge particle. Now what is minority in this p side? The minority are the electrons. So we can say that this electron will come into this battery. So there will be a small amount of current. Fine. So there will be a small amount of current. Similarly, this is the negative. So this negative will repel what? The majority charge particle. Now what is a majority in the n side? The electrons are the majority in the n side. So they will try to repel here and they will attract the positive, that is the hole. They attract the holes. So what is happening now? So the current is flowing. Now the small amount of current, because the minority are very small in number. There will be a small amount of current which is flowing due to the minority charge carriers. So let us draw the curve now. So you can see here, this is the curve. This one is a voltage, because we are applying a voltage. So this voltage should be treated as the independent variable, and this is the positive voltage. So obviously we are going to obtain the current in the positive direction, and our curve will be in the first quadrant only. So okay, so this current will be in milliamperes, and this is the voltage, because you are going to apply here some resistance you are going to apply. You cannot directly apply the voltage to a PN junction diode. You will have to apply a voltage in series with a resistance, and that will be in kilo ohms. Let us say it is 1 kilo ohm. So in that case it will be milliamperes. Fine. So now what is going to happen? So you can see the barrier potential slowly and steadily, when you are increasing the voltage to the effective voltage, because you can see here initially when the voltage has not been applied, that time you are having the barrier potential, and this is VD. So when you are applying a VD, so there will be a difference. The effective voltage will be what? The effective voltage will be VB minus VD. So if you are going to increase the voltage, now suppose if you have taken the silicon diode, so for silicon diode it is 0.7 minus VD. So you have to increase the voltage VD from 0 to some value. Okay, so now we will increase VD to 0.2 volts. So what is the effective voltage? 0.7 minus 0.2, so 0.5. So this much barrier potential will exist here. And because of the barrier potential, there will be a depletion layer. Now again, to increase the voltage, because we are having a variable power supply, so VD will be equals to what? 0.5. Let us say, so 0.7 minus 0.5, that will be 0.2. So now when VD will be equal to 0.7, now we'll say this as a 0.7. So 0.7 minus 0.7, 0. So this is on the verge of the breakdown of the depletion layer. So at this point, the depletion layer is going to break down. So what is going to happen that when the depletion layer breaks down, the current, the majority carrier, that is the holes, will move from P side to the N side, and similarly the electrons will move from N side to the P side, because here you are having the electrical field, and electrical field is going to attract the electrons and the holes accordingly. So after this cutting voltage, we can say, after this voltage, when the depletion layer breaks down, the voltage at which the depletion layer breaks down is called the cutting voltage. So for the silicon it is 0.7. So I think you can see here this is 0.7, and after when this voltage has reached or attained, the current increases sharply. We can say the current increases sharply. Okay, I'll draw it. The current increases sharply in the exponential fashion. Why does it in the exponential fashion? Because you can see here I will be equal to I0 e to the power of Vd upon eta Vt minus 1. And this Vd is a positive voltage, so this this term is a positive quantity. So e to the power of positive quantity will be a very, very high value. E to the power of positive quantity. Now suppose if you take e to the power of 10 plus 10 and e to the power of plus 10. just a minute, e to the power of plus 10 and e to the power of minus 10. So which one is larger and which one is smaller? You just check it out. This e to the power of 10 and e to the power of minus 10. This value is nearly equal to 0 and it is highly greater than 0. So this term is very high as compared to 1. So we can neglect the 1 value. Fine. So in that case, what is the current equation? IF will be equals to I0 e to the power of VD upon eta VT. VD means for forward voltage. Fine. So now why this is the small amount of current is there? This small amount of current is because of the minority charge carrier. It's a very small in number, and this current, just a minute, and this current, where it is gone, okay, and this current is due to the majority charge particles. So you can see that your current is comprised of the two charge carriers. The first one is the minority charge carriers, which is here, and this is the majority charge carriers. Now the current which is exponential is due to the majority charge carriers, and this is the constant current, you can see, because you can see that depletion layer is there, no, and the majority will only flow from P to N. There is no other way, no, there is no other way. So this is the curve which has been obtained in the forward bias. Now what will happen in the reverse bias? Now what will happen in the reverse bias? We'll just check it out. So in the reverse bias, you will have to apply a negative voltage. In the reverse bias, you will have to apply a negative voltage. So when you are applying a negative voltage, so when you are applying a negative voltage, so what is going to happen? This is negative and this one is positive. I think I will have to write here positive and negative. So what is going to happen? A negative electrical field is going to be present, is going to exist here. This one is positive. This is now the external electrical field is from, you can see here, from, this is from N to P. So external electrical field, and this is the internal electrical field. So what you can see now, both the fields are aiding each other, or you can say supporting each other. In forward bias, they were opposing each other. Now they are aiding each other. So what is going to happen? Now you can see that this negative will try to attract the majority charge carrier. This positive will try to attract the now this positive will try to attract the electrons which are majority in number. So basically now the majority charge carrier will be swept out. Now the majority charge carriers will be swept out, and slowly and steadily the depletion layer increases. Slowly and steadily the depletion layer increases. So all these charge particles will be swept out now. Will be swept out and will be, just a minute, will be swept out. So now I think this is for the forward bias will be swept out. So you will be having this current. You will be having this current in the reverse bias condition. And I think from the equation also you can see that I will be equal to I0 e to the power of what? Vd upon eta Vt minus 1. So now in this case, I think the diode voltage is in this case the diode voltage is negative. When diode voltage is negative, this term is this term AB minus VR upon eta Vt is very small as compared to 1. So you will have to neglect the value. So this will be, I will be equal to minus I0. So this is the way you can have the VI characteristic. So the constant value will be there. The constant value will be there. This because there will be a flow of only minority charge particle, because they are attracting the majority charge carriers, and the minority charge particles will move here now. Fine. The minority charge particles in P side will be electrons, and in the N side will be holes. Fine. So only they will diffuse to a junction. The other charge particle will be swept out. So in this way we can understand the VI characteristics of the PN junction diode.